Are we ready? Okay. So we've got this cubic 6-inch cube of ice. Okay. If it's 33 degrees in this room, this ice is going to melt, isn't it? But it's going to melt a lot slower than it would melt if it was 70 degrees, and a heck of a lot slower than it would melt if it was 100 degrees in this room. The rate at which this ice would melt is going to be purely a function of the thermal energy available. All right. Now, it's pretty much a straightforward physics problem to calculate the thermal energy available as a function of the ambient temperature and the mass of ice, and then how long it would take to convert that ice into liquid water. When the scientists began to look at the total mass of ice that was in place at the peak of the last ice age, and then they began to calculate the amount of time during which the ice disappeared, they were faced with a real conundrum. This was first confronted in the mid-70s. It has not been resolved to this day. And that essentially is the energy requirements for dispersing and melting that ice as quick as it was. They did some calculations. One of the things they did was they said, okay, most of the ice basically covered all of Canada, from the Atlantic to the Pacific and from the northern United States to the Arctic Circle. Oh, by the way, there was a curious thing. It's very possible that the North Pole itself was not glaciated. Most of Alaska was not glaciated, and most of Siberia was not glaciated. So the old model of the ice age was that the ice mass grew essentially symmetrically around the North Pole, extending in equal directions more or less from the North Pole in all hemispheres, but it is apparent now that that's not what it did. The entire ice mass was totally lopsided. Offset, essentially the center of the ice mass was about 30 degrees offset from the present pole, which raises another question that I'm not going to get off on that tangent right now, but it raises a very interesting question. Well, that's one of the implications. You know, while all of Canada and the northern United States was buried under a mass of ice, one of the coldest places on the entire Earth now, which is Siberia around the Arctic Circle, was grassland and inhabited by this incredible array of megafauna, which of course no longer exists. Megafauna, big animals like mammoths and saber-toothed tigers and dire wolves and 600-pound beavers and 16-foot tall ground sloths and on and on and on.
Where Siberia is now.
Yes. Of course, all of the unglaciated United States was also inhabited by this incredible megafauna. This area, of course, here was not under the ice. If you go north of here, basically just the other side of the Ohio River was where you would get to the southern margin of the ice cap, what was called the Laurentide ice cap, which describes the ice cap that was centered over Hudson Bay, this area right here. In fact, the entire topography of the United States was created either by the ice or the melting of the ice. The Ohio River Valley is where it is now because the meltwater essentially followed the southern margin of the ice sheet and created this valley. You know, the Mississippi River is where it is because the meltwater pouring off of the ice sheet on its way to the Gulf and so on. In fact, most of the river valleys in North America are 10,000 years old or less. So if you go to the unglaciated part of North America, like North Carolina, for example, the only modern analog to the density and diversity of large animal life that exists on Earth today is the Serengeti Plain of Africa. In North Carolina, in fact, in the United States, southeastern United States, throughout the late Pleistocene and throughout the end of the last ice age, down till 10 or 12,000 years ago, there were 3 species of lions that lived in Georgia and North Carolina. There were 3 species of elephants. There were camels. Castoroides, the 600-pound beaver, was very prevalent throughout North and South Carolina, Georgia, Florida. Mastodons, Glyptodons, which were cousins to modern-day armadillos, except that they were the size of Volkswagens.
So they found remains, they found fossils of these things?
Oh yeah, oh yeah. Every one of them, that's, what?
Where are they shown? The elk.
The Irish elk. I don't know if the Irish elk was native to this area, but there was an animal called the Irish elk, and it had an antler span in excess of 12 feet. Its shoulder, I mean, I've got artists' depictions of all of these guys in my slideshow, if you're interested in seeing them. What I've been doing is, I'm not quite done with this yet, but I've been taking these animals, and then I've been superimposing an outline or an image of a person, so you can kind of see a sense. Oh, then there was the Ursus spalaeus. Ursus spalaeus was essentially a 2,000 pound bear. And it was the biggest, it was a meat eater. It was the most ferocious predator of the Ice Age. And they were long-legged. They estimate they could probably run in excess of 40 miles an hour. There were dire wolves whose jaws were almost twice as big and massive as a modern-day timber wolf. There were, I mean, on and on. There were several species of woolly rhinoceros. There were, I think 3 species of camels that lived in North America. There were ground sloths that, let's see, when they stood up to feed, their heads would be well above that turnbuckle bar up there. 16 feet. Picture, I'm 6 feet tall, so double my height and then add 4 feet to it. Okay, right at the end of the last ice age, they all disappeared. In fact, it probably is the greatest paleontological mystery since the disappearance of the dinosaurs. But the irony of it is we know more about the disappearance of the dinosaurs that happened 65 million years ago than we do about the great Ice Age megafauna of 12,000 years ago. It's true. We know less about what caused their disappearance a mere 12,000 years ago than we know about what caused the disappearance of the dinosaurs 65 million years ago. Again, it's one of the great unexplained scientific mysteries of our time. But it's tied right in with the explanation of what caused the end of the Ice Age and the rapid melting of the ice. What the climatologists referred to as the energy paradox. And essentially the energy paradox, this is what they did. They said, where on the planet now do we have the greatest amount of thermal energy available to melt ice the quickest? Well, the answer was tropical oceans. So they said, okay, let's do a calculation. Let's imagine we can take the whole ice cap, move it to the tropical oceans, flanking the equator. How long would it take to melt? Answer, 15 to 20,000 years. Okay, supposing that we melted the ice cap where it was, which is Canada, we used the amount of thermal energy available that's now available in Canada, how long would it take to melt? Answer, minimum 30,000, perhaps 40,000 years or longer. How long did the ice actually take to melt? No more topside. 90% of it melted away in 3,000 to 4,000 years or less. This is what they refer to as the energy paradox. The energy paradox was first discovered in the mid-70s and has not been resolved to this day.
Any theories?
Oh, there's lots of theories, but really none of them make a whole lot of sense when you scrutinize them. And here's the problem with most of the theories and why they're not getting anywhere. Virtually every theory proffered was based solely on terrestrial mechanisms. Volcanism, changes in the salinity of the ocean, shifts in ocean currents, shifts in the jet stream. The problem was one guy would come up with a theory and then everybody else would rip it to shreds and put it right back to square one. There will be no satisfactory resolution to this paradox until scientists start thinking outside the box and realize that our planet, our little planet, is actually part of a cosmic ecology, and that there are cosmic forces at work that have manifested themselves in the changes on our planet. Once they begin thinking and recognizing that there is a much bigger scale of things, then they will begin finding answers to some of these puzzles, but not until then.
What's an example of a cosmic influence?
A cosmic what?
Influence, you mean like an asteroid?
Asteroid, changes in solar output would be another good one. Solar flares, changes, stars going supernova nearby in the galaxy. There's a number of them. Changes in the flux or accretion rate of cosmic dust, which would be a function of how much material is being delivered to the inner solar system. There's a number of things that I think could provide very fruitful possibilities for coming up with explanations.
Scientists haven't factored that in?
No, a few of the more adventuresome ones in the last 10 years have begun to propose models of Earth change that involve things outside of the Earth itself. So far, though, the mainstream is so entrenched in their dogmas, though, that they're not really getting anywhere. They have the models, and they don't want to really have to, it's neat. Here you've got this system, but to suddenly say, oh my gosh, we have to now look at it as part of a whole solar system, that, our star, our sun, may be variable in its output. In fact, as we get along into it, I'm going to show you very specific ancient traditions that would point directly towards that conclusion, that the sun is variable in its output, that there are pulses where the cosmic material becomes much denser, and there are scientific models that are explaining some of this. For example, about 5 or 6 years ago, astrophysicists began to realize that there was a cycle caused by the tempo of the outer planets, and outside of Neptune is this zone called the Kuiper disk. It's a zone that consists of billions of comets that were left over from the formation of the solar system. Outside the zone of the Kuiper disk is a sphere called the Oort cloud. The Oort cloud is billions, perhaps even trillions of comets that essentially are hovering in a very, very quasi-stable or quasi-chaotic orbit between our sun and the nearest stars. Basically, what the astrophysicists are beginning to think now is that if you look at, let me draw a diagram up here. Suppose you have a situation like this. We have a hill and we have a valley. And I take a ball or a marble or some kind of nice round sphere and I put it right up there. And as long as you don't touch it or breathe on it or disturb it in any way, it'll sit right there delicately poised. Now, suppose I put another ball or marble or whatever down there. What we have here is a stable situation, and here we have a quasi-stable situation. A perturbation on this, and it's going to quickly return to its stable position. Any kind of perturbation on this at all, and it's going to depart from its present condition, move chaotically to a different situation where it's going to restabilize. Or if there's also occupied by another marble or ball down here, it will collide with that and induce chaotic repercussions. Now, if you think of these comets in the Oort cloud and the Kuiper disk, they're in a situation very much like this. It doesn't take much of an input at all to cause them to dislodge from their positions. Now, if you cause this to dislodge and it starts moving, obviously it's either going to move this way or this way. Essentially what happens is you could think of it like this. Think of this position here being a gravitational well at the bottom of which is our sun. Over here is another gravitational well at the bottom of which is a nearby neighboring star. Something causes or perturbs the stability of this comet in this position, it's going to begin migrating or moving one way or the other. Well, Michael Rampino and Richard Strothers and some other geophysicists and astrophysicists began looking at models of the galaxy, and they realized that there's a number of things within the galaxy itself that could cause disturbances to this delicately arranged bubble or sphere of comets that resides out there in the Oort cloud. For example, the galaxy as it rotates bobs up and down. There are suborbital systems within the galaxy itself. In fact, I'm going to at some point introduce you to an esoteric concept having to do with subgalactic orbital systems between our sun and the center of the galaxy. Very interesting stuff. But galactic perturbations or disturbances on a galactic level tend to dislodge comets from the Oort cloud, and they begin to go in a spiral journey, working their way, essentially falling towards the sun. A certain percentage of these, say half, will tend to fall into relatively stable orbits outside of Neptune, between the Oort cloud and the zone of the planets, generally in a more or less flat plane. This is what's called the Kuiper disk. Now, on the inner zone of the Kuiper disk, the comets tend to be, again, very delicately balanced. They're quasi-stable. So what the astrophysicists realized within the last decade or so, they started doing models, and they realized that when the large massive outer planets, Uranus, Neptune, Saturn, and Jupiter, form alignments on the same side of the sun, their combined gravitational fields are enough to begin dislodging comets that are on the inner zone of the Kuiper disk. What now is the evolution of those dislodged comets? They begin migrating towards the inner solar system. Now, when a comet is way out in the Kuiper disk or the Oort cloud, it's in total hibernation. It's like dry ice almost. It's total deep freeze. But as it begins its journey towards the inner solar system, as it comes in and passes first Uranus or Neptune and Uranus and Saturn and Jupiter, the gravitational fields of the planet first begin to accelerate the activity within these comets. Now, a comet has been likened to a frozen snowball. It's mainly composed of deep frozen water ice, but within it are all kinds of things, from dust to rocks to volatile gases to amino acids to perhaps even the primordial material for the creation of life itself. But these comets begin moving in, and here's what happens, and here's the interesting thing, and I'm going to give you copies of this material because it relates so directly to what we're learning about in here with dealing with ratios of geometry and so on. The spacing of the planets, as it turns out, is exactly what you would want if you were going to design a system so that the outer planet, see, here's the thing. Once the comet becomes dislocated from the inner zone of the Kuiper disk, it then can fall into the gravitational field of Neptune. Now, here's what Neptune will do. You picture, here's a planet with a big gravity field. And it's going around the sun, and here's a comet up here orbiting, and the planet is coming up behind it. And it's exerting this strong gravitational pull on the comet that's moving ahead of it. Well, it's going to be applying, essentially putting the brakes on that comet. As the comet slows down, what does it then do? It falls towards the sun. And in fact, the gravitational pull of Neptune is just enough to slow a comet down so it will fall into the next orbital shell and can get caught by Uranus. Now, the converse of that is if the planet is ahead of the comet and it's moving along, it's now going to accelerate the comet and it's going to sling it out like a slingshot almost, or when we played, remember what the boys used to play on the playground? They probably don't let boys play that anymore on the playground, but We used to lock arms, about 20 of us, and we'd start in a big, and the guy in the end, as soon as his legs would be up parallel to the ground and he'd be flying around. Yeah, you know what I'm talking about, don't you, Jim? Well, essentially you can picture that that's what's happening to these comets that get caught in a gravitational field of a planet moving ahead of it. They're accelerated. Well, as they're accelerated, they jump outwards, okay? Roughly the probabilities might be 50-50. If you've got 100 comets that fall into the orbit of Neptune, 50 of them will eventually get slung back out and 50 of them will get handed off to Uranus. Uranus happens to be just the right distance to do the same thing again and hand 25 of those comets off to Saturn. Saturn then can hand half of those comets off to Jupiter. Jupiter, you know, the big guy, he's going to take those comets and he's either going to sling them right on back out to the Kuiper disk, or he's going to slow them down to the point where they then begin to fall right into the sun in a big spiraling arc. Now, as they do this, and as they fall towards the sun, they begin heating up. And it's like these deep frozen hibernating snowballs come to life. It's like turning on the ignition. They begin rolling and tumbling in space. As they heat up, pockets of volatiles explode and things spew out, and they begin discharging their cargo. They begin, it's a picture almost, you know, picture a dump truck barreling around the highway loaded with stuff in the back, and that stuff starts flying out and creating a dust cloud, and stuff starts flying out and rolling down the road in big chunks. That's what these comets do. They now go through a whole life cycle. They've been in deep frozen hibernation for eons of time, probably for 4.5 billion years. But now they come in, they come to life, and they begin literally going through a whole cycle. And what they do now is they begin orbiting the sun. They'll usually get caught between the sun and Jupiter typically. They'll go into highly elliptical orbits until eventually they completely disintegrate, or they eventually fall into the sun, or they're intercepted by another planetary body, including Jupiter. And some of you probably remember in '94, when Shoemaker-Levy 9, we human beings got to witness the final demise of a comet. When it broke into 21 pieces, the astronomers made a prediction. After 3 months of observations, they calculated the delicate geometry of its elliptical orbital path, and were able to conclude that yes, in the second week of July of summer of 1994, all 21 of those pieces were going to collide with Jupiter. And just mathematically precise, their predictions were right on the money, and we were able to witness 21 pieces colliding with Jupiter.
Did you see a change in the Earth's environment as well?
No, we didn't see any change in the Earth environment. Now, however, had those 21 pieces hit Earth, we would not be having this class today. Okay, now, here's what can happen. A big comet, and comets can be big. I mean, big relatively speaking. You might have a big comet nucleus. Hale-Bopp, you remember from a few years ago, was considered to be a big comet. It had a nucleus about 50 or 60 miles in diameter. Well, if a comet like that begins to break up, it can produce millions of pieces. Now, in 1908, a little piece of Comet Encke came in. This piece that came in 1908 on a summer morning, June 30th, 1908. Came in, it was about 150 feet in diameter. Now, a comet the size of Hale-Bopp could produce millions and millions of pieces the size of this Tunguska object, it was called, as it was called. It came in 1908. That object came in over the Taiga Forest, which is just on the southern, just below the southernmost range of the tundra. It descended at an angle to a depth of 5 miles, and at that point, it blew up. When it blew up, a blast wave passed out from the epicenter of the blast. the blast began to just mow the trees down flat. From ground zero below the blast zone, it was an atmospheric blast, the radius of total destruction went out, was actually an elliptical shape. In some directions it went 20 miles along the short axis of the ellipse. Along the long axis of the ellipse, it was nearly 30 miles from the epicenter. It was as big, roughly, even in fact probably more powerful than the most powerful hydrogen bomb ever detonated by human beings, which was 60 megatons detonated by the Soviet Union in 1963. What we see there is that in our testing of nuclear weapons, the most devastating and destructive and powerful weapon that we ever created, human beings ever created in a nuclear arsenal, was basically the bottom end of the cosmic spectrum. Okay, now, a comet comes into the inner solar system, a large comet, and begins to disintegrate. And it litters the entire solar system with chunks and debris and dust. Here's where you can have all kinds of terrestrial consequences. Even if no pieces collide with the Earth, it's very possible, if not probable, that under a condition like that, and we're not talking about some of these cycles probably produce not just a single comet, but multiple comets, that the inner solar system, the region inhabited by the Earth in its orbit, becomes just littered with cosmic dust. Now, Earth is like a big magnet passing through this field of cosmic dust. That cosmic dust accretes to the Earth. It goes into the atmosphere. It increases the optical density of the atmosphere. As a consequence, it drastically reduces the amount of solar radiation reaching the Earth. And now you have, to me, the most plausible mechanism for starting an ice age. Starting one. There's still some inherent problems, mainly because in an ice age you have to not only simultaneously lower the temperature, but you have to increase precipitation, which is a complete contradiction. Because in order to increase precipitation, you have to increase the heat, because heat is what drives the hydrological cycle. So all of this stuff that I'm getting at has to do with the fact that what scientists, I think, are now recognizing is what ancient peoples knew all along, is that Earth is part of a cosmic system. And when you begin to look at the ancient architecture and the layout of cities and temples and cathedrals and churches, invariably, in every continent, in every ancient culture, they did the same thing. They recreated a map of the heavens on the surface of the Earth. Now, when I show you the slideshow after dinner, some of this may become more apparent to you because I have this stuff graphically demonstrated in there. But when those scientists looked at the motion of Comet Shoemaker-Levy 9, studied its motion for 3 months, were able to predict that a year hence, to the day, even to the time of day, that those pieces were going to start colliding with Jupiter. What they did was they used the geometry of the conic sections. They had to have two things, basically. They had to have the geometry of the orbit, and they had to have the timing. Once they had the geometry of the orbit and they had the timing of the thing, they could then begin to make mathematically precise predictions. And that's exactly what they did. In order to do that, in order to get the geometry of that ellipse and to be able to discern the timing of it, they had to have what an astronomer or astrophysicist calls a celestial reference frame. They had to have certain points in space that all of this movement could be referred to. Okay, the points that constitute the framework of this celestial reference coordinate system happen to be exactly the same points that were defined and demarcated in all of the ancient astronomical orientations of all of the ancient cultures on every continent, just by coincidence. We are using the same reference frame today that is developed from the solstitial line and the equinoctial lines, which were defined with tremendous accuracy by the layout of the ancient structures in the ancient temples. We're still using a system today to predict motion, celestial motion, that is thousands and thousands of years old. To me, this is highly significant. And it points, to me, it points in a direction of at least one of the reasons why ancient peoples were so obsessively interested in the sky and celestial motion, and being able to track with a high degree of accuracy the motions of the sun and the moon and the planets. Because, as you will see in the slideshow, we have been blessed with an anomalously stable period of climate. In fact, from the models of climate change that we now have, which are getting very, very accurate, they're based upon ice cores taken from the Greenland ice sheet, where they drilled down, European team and American team drilled down in the early 90s. It took them 5 summers to do it. They drilled through 2,000 meters of ice, complete ice cores down to bedrock. They extracted those ice cores. When you take an ice core like that, it's very much like looking at a tree ring. Tree ring will give you a year-by-year graph almost of what was going on around that tree in the environment. If there's a lot of rainfall, you're going to have a nice big summer growth. If it was a drought summer, it's going to be a skinny little line. Well, in the Greenland ice cores, essentially what you have is each year's snowfall forms a layer. And as you go down core, you've got hundreds and then thousands of layers. Scientists go in and they analyze those layers and they look at what's in those layers. And they see things like dust, they see things like soot, they see things like oxygen isotopes, which are directly a function of temperature and temperature changes in the ocean. And what they have seen is that out of the last 250,000 years, and you're going to see the graph for yourself after dinner, and the graph is as graphic as it can be. Since the end of the last ice age, we have enjoyed a period of climate of unprecedented stability. There has been no period of climate in the last 250,000 years remotely as stable as the period of climate we've been enjoying for the last 8,000 years. I think this could have implications.
What do you attribute it to?
To what?
Stability.
A number of things. For one thing, think about this. What was I describing as being perhaps one cause of climate instability? Would be the flux of stuff in Earth space. Well, let's say you have a barrage of stuff coming in. As it goes through its life cycle, that stuff is eventually cleared out, isn't it? So if you have a cycle of comets coming in, it might take 10,000 or it might take 100,000 years for those to fully disintegrate and then for it to be cleared out.